Hello, today we'll be going through an introduction for inner products and norms from linear algebra. So let's first start with something we're all familiar with. It's multiplication. So take 2 times 3 equals 6. A better way to think about multiplication is where 2 and 3 are each one-dimensional vectors. So 2 times 3 is really 2.3 equals 6, the scalar. It's good to think about it this way because dot product is really just a generalized multiplication for vectors. As we can see here, v and w are both vectors, and v dot w is the multiplication for each element summed. A good geometric intuition for dot product is shown here. Projections. Say v and w are these arbitrary vectors that I drew. V dot w is really finding the component of v in the direction of w. So you can think of v projecting onto w, and the result is a scalar of the length of this vector, of this segment. Another good intuition for dot product is looking at it as a linear function mapping Rn to R, where n is the number of vectors, number of elements in the vector. So this is a way you can write it, where it is a 1 by n matrix times an n by 1 matrix, and so given and resulting in a scalar. Note, it's very important that you know the dot product of a and b, which are vectors, equals to 0 if a and b are orthogonal to each other, meaning a and b are perpendicular. The geometric intuition for that is if a and b are perpendicular, there is no component of a in b, and there is no component of b in a. This will be important later on. And we also notice that the length of a given vector v, assuming it has two elements, v1 and v2, the length of v would be the square root of the of the dot product to itself. Now that we have went through multiplication and how dot product is a generalization of that, we will now see that inner product is a generalization of dot product in all spaces. Inner product is really abstracting the idea of angle, which is the inner product, and length, which is norm. We will talk about that later. And the notation for inner product is written as such. This could be defined as a dot product, so you can see this as v dot w, but inner product is more general than that, and we can define it however we want in different spaces, even function space, with restrictions though. So now we'll see the restrictions. Here's the requirement for defining an inner product. These are more formalizations. I will go through them much faster. So the first is bilinearity. If you look at it from afar, it might look like factoring in algebra, which you would be right. It's pretty much like factoring, but in both directions, as you can see, both of these. And the second is symmetry. I think it's quite obvious what it is. And number 3 is positivity, where inner product of v by itself is greater than 0, and it's only 0 when v is 0. So it has to be positive. And here's an example for what is an inner product could be defined as. These are commonly known as weighted inner products. As you see, the only difference between these inner products and dot products, which is a type of inner product, is that you're weighted the second term and the third term. And so these are commonly used in statistics where, for example, there's an outlier in your data and you don't want to overcompensate for those outliers. Instead, you want them to weight less than the majority. this is where it will be used. And important, why is inner product important? It is important because we can define different inner products, and we know which are orthogonal to which. So if we define an inner product for this using this definition, and we find two vectors w and v which are orthogonal, it is obviously will not be orthogonal in our Euclidean sense, but it will be orthogonal in this inner product. So it's in different spaces that we're defining. And orthogonality is important because later on, if you know, you can form bases, orthogonal bases, and orthonormal bases, and orthogonal matrices. Now that we have dealt with inner product, let's talk about norm. So let's again start with something we're all familiar with, length. The length of something. It's very intuitive. And the length of a vector is where it comes into play, is really a generalized version of length on a 2D plane where it's coordinated. So in 2D, it is, as we know, similar to distance formula. The distance between 2 points. This is x squared plus y squared, square root of them. And same applies to 3D. And 4D would just be adding another term, w. So norm is a generalization of length. So as we talked about in inner product, you are kind of defining a new rules for a new space that is different than the grid that we're used to. And so in this new space, we need something to define how far are 2 points from each other. So norm would be the definition of that. The notation of norm is this. Some also writes it with just one line, but most textbooks uses 2 lines. Notice that the norm of v, that is the length of v on this new inner product space. Inner product space, by the way, is a space where an inner product is defined. So v, the length of v on this new inner product space is the inner product of v to itself square rooted times 1/2. Since this is a definition of inner product of v by itself for dot product. Thus, this is because the definition for norm includes inner product. We know that each inner product has a norm. So when you define any inner product, weighted or not, or otherwise, there arises a norm with it. But the converse is not true. There are norms out there that is defined without a proper definition of its inner product. So how to conceptualize this concept of inner product space? As each inner product space has its own definition of inner product and norm. You can think of it, how I think of it, is as there are spaces that are not exactly in a grid, like in Euclidean. You can think of you can transform these spaces with linear transformation into maybe a grid is 5 by 4, or it might be in a it might be a little twisted, like linear transformations. And in those spaces, you need a definition for angle and length, and that's how inner product and norms arises. In an even more humanized concept, you can think of inner product spaces as different countries have different rules, different laws, and so the inner product space is different spaces that have different laws that you could define. And that is for all today. Thank you so much for watching. Please let me know if you have any suggestions, and what topics you would like me to cover. Thank you.